There. Just about finished. What's the matter with Boffin? Hey, why haven't you had your milk? It's curdled. It was fresh a few minutes ago. Ugh, what's that smell? Ah, vinegar must have done this. It's not a very nice chemical reaction, is it, Boffin? Get you some more in a minute. Duty calls. How can I help?
Stella, we've been reading this book about insects, and there's something here that's a bit confusing.
Yeah, it says that you can treat a wasp sting with vinegar.
But you treat a bee sting with bicarbonate of soda.
Yes, but if the stings are the same, why do they have different cures?
Maybe it's because vinegar and bicarbonate can help cure infection, and so kill the stings.
Maybe they're not the same. Stella, has it got anything to do with what's in the stings?
I think you might be onto something. Leave it with me. So, two things that seem the same, but need to be treated with very different solutions. So what makes a sting sting? Well, chemicals. So the chemicals in a wasp sting must be different in some way to the chemicals in a bee sting. Now, look at these two groups of chemicals. It may not look like it, but all the chemicals in each group have something in common. Now, these belong to a group of chemicals called alkalis, and these belong to a group called acids. Now, many everyday chemicals are either acidic or alkaline. But how do we know which is which? Must be an easy way of telling. It's time Femi investigated.
There, finished. Now, believe it or not, I've actually carried out lots of chemical reactions. Come with me. These shampoos, conditioners, bubble baths, in fact, all of these toiletries are made out of chemicals. Now, they may be acidic, neutral, or alkaline. What I want to investigate is how you can tell which are which and why it should matter.
I've come to see Patrick Love, who's in charge of developing new toiletries for Britain's biggest chemist.
So why does it matter if a soap or toothpaste is an acid or alkaline?
Well, your body is made up of a lot of different chemicals. Some of them are acidic, some of them are alkaline, some are neutral. And so it's important that the products don't react in the wrong way with the chemicals in your body.
Right, but how can you tell then if something is either an acid or alkaline? Do you just guess?
Well, no, we don't actually. We've got something called universal indicator paper, and it comes in these little packs here. And this changes colour depending on how acid or how alkaline, whatever it is. We've got some ordinary cola here, and if I dip this in, what you can see there?
Ah, now that's gone quite pinkish, sort of orangey colour.
Here I've got a table that shows the range that you can go through, and it goes through from red, which is acid, through to blue.
So that must be an acid?
That is right, that's an acid. So an acid will turn towards the orange or the red colour. And here I've got some ordinary household bleach, and then if we test this again, what do you see there?
Wow, now that's very blue, greenish. So that's an alkaline.
Alkaline.
Right. So can we do some more testing?
We certainly can. I've got a nice one for you.
OK.
Perhaps you'd like to just test your saliva. So I'll tell you what, if you'd like to put a little bit of saliva in, in there, then...
Right.
Let's see what we get now. There we are.
That's
now,
green.
You see there? That's very slightly green. What that shows is slightly alkaline.
Good match.
Yeah. Why don't have a bite of one of those oranges and get a nice bit of orange juice in your mouth?
OK, tough job, but someone's got to do it. Very juicy.
Now, if you have another spit, if you don't mind, in there.
Excuse me. OK.
Right, so how's that gone?
Slightly orange.
Yes, that's right. So that's on the acid side, OK? And when the citric acid gets in your mouth, it turns it to acid.
Right.
Now, there are other acids that hang around in your mouth, and although the saliva can neutralise these acids, some it can't, and that's why it's important to brush your teeth.
So it looks like I'm going to have to watch the acidity in my mouth and carry on spitting.
Not only can indicators be used to see how acid or alkaline a product is, they can actually be used in the product. Now this is mood lipstick, green lipstick. But if I put it on my hand, it goes pink. Now why? Does my mood cause this change? Well, let's see. I'll put some of the lipstick on these pieces of paper. Now, this piece of paper is going into lemon juice. That's acidic. The next one is going into soda water. That's also acidic. Now, an alkali, baking soda. And finally, another alkali, oven cleaner. Now, this shows that the colour change is due to an indicator in the lipstick which reacts in the same way to the acid or alkali level present on the lips. So maybe it doesn't have anything to do with mood after all. Perhaps it's just a bit of fun with indicators. You can make indicators out of certain foods. For example, this is cherry juice. And if I add alkali, it turns purple. Now, other good homemade indicators are blackcurrant juice or beetroot juice, but the best is red cabbage, which turns acid pink and alkali green. Now, in her investigation, Femi was using a universal indicator. And this is a mix of a number of different indicators, and it's particularly good because of the range of colours it produces. If I put universal indicator in orange juice, it turns slightly red. But if I put it into lemon juice, it turns very red. And this means the lemon juice is more acidic than orange juice. Now, if I try these experiments on lots of different substances, I end up with all these colours, from the very red at one end to the very blue at the other end. But is the dark red, the very acidic, stronger than the dark blue, the very alkaline? Well, let's see, shall we, with the help of these two volunteers. Now, I've got to be very careful here. This dark red is sulfuric acid, and this is what it does to Kevin when concentrated. Not very nice. But look, this dark blue, caustic soda, is very alkaline, and look what it does to Kevin's brother when concentrated. Just as nasty. So, both are very strong, but in different ways. So maybe it's better if we look at our scale of colours like this. If we number them from 1 for a strong acid to 14 for a strong alkali, with 7 in the middle, meaning neutral, neither acid or alkali, then we have a scale, known as the pH scale. And the pH scale is how acidity and alkalinity are measured in scientific terms. I think Femi is looking into how else it can be used.
These science in action investigations don't half give you an appetite, so it's great to be able to sit down, relax, and enjoy a slap-up meal. Here comes the first course.
Perhaps this might be of use to you.
I think I feel an investigation coming on.
I've come to one of the biggest food companies in the world, and they use this factory to test out new recipes. Malcolm is one of their top scientists, and he's invited me to try 2 samples of soft drink, fish, and vegetables. They were all made on the same day, but I can tell just by looking at them that one sample of each seems fine, while the other has definitely gone off. And as for the smell coming off one of the fish...
I can feel my breakfast.
Right, now this is a perfectly good herring.
Right.
It's in reasonable condition.
Lovely.
And this fish...
It stinks. It is so gross.
Fish is oozing some horrible white fluid. I really would not like to open this
I'm
fish.
not even going to go there, Malcolm,
No,
okay?
no, there's quite a strong smell coming, even it's been wrapped in 2 plastic bags, and it's still smelling through all that lot.
If they were all made on the same day, why some stayed fresh and the others gone off?
Well, that's where the chemistry comes in. As a hint, this is a pH meter.
Right.
So we need to test the pH of all these foods.
Using the pH meter, it's obvious that the good samples had a much lower pH. They were more acidic than the ones that had gone off. So what's going on?
Well, what makes food go off? The answer's bacteria. Bacteria love growing at neutral pH, near pH 7. And as the pH gets more and more acidic, the bacteria grow less and less well. Now, I can show you this. If you look over there, we have a series of flasks containing soft drinks ranging from pH 7 to pH 2. Now, we put bacteria in all of these flasks, but as you can see, they've only grown in pH 7, pH 6 and pH 5, forming this thick cloud of bacteria. At low pH, pH 4, pH 3 and pH 2, it's still completely clear, and the acid in the soft drink has killed those bacteria.
So you put acids into food. Isn't that dangerous?
Well, no, not if you know your pH scale and you carefully measure the amount of acid you put in. And this is what we do to all our foods.
So the reason that some of the products have gone off is that they have a pH close to 7. That is neutral. And they now have bacteria growing in them, making them seriously disgusting. The foods with a lower pH, that is more acidic, have stayed good and are still edible.
So, you could make up cans of my favourite food, prunes, spinach and custard surprise. And with the right pH, it would stay fresh for months.
Well, we could make up cans of prunes, spinach and custard surprise, but to be quite honest, we wouldn't want to. It sounds absolutely disgusting.
Speak for yourself, Malcolm. It's delish.
Here we are, Boffin. Some fresh milk and not a drop of acidic vinegar anywhere near it. Now, if an acid reacts with an alkali, a number of things can happen depending on the two you're mixing together.
And one useful one is when you mix the right amount of acid, this one has a pH of 4, with the right amount of alkali, this has a pH of 11. The acid and the alkali neutralise each other.
Neutralise? Ah, that must be what happens to the sting.
So, if a wasp sting needs vinegar, which is slightly acidic, to neutralise it,
it must mean that the sting itself is slightly alkaline.
So a bee sting must be acidic because it needs the alkaline bicarbonate of soda to neutralise it.
Look, it says here that bicarbonate of soda is also taken for indigestion.
That's because it's bubbly and helps break down the food in the stomach.
or somehow it makes all the windy gas come out.
Maybe it helps because there's some kind of chemical reaction. And that means we've got acid in our stomach.
No, we don't.
Stella, what is in our stomach?
I can show you. This is a model of the stomach. And inside, there are lots of different chemicals, including, would you believe it, hydrochloric acid, which is a very strong acid with a pH of 2.
And that acid is there to aid digestion.
Now, if the acid builds up, you can start to feel unwell, a bit windy, you know the feeling. So, to calm the stomach, you have to neutralise the acid by adding an alkaline substance. Now, these indigestion tablets contain bicarbonate of soda, which is the same sort of alkaline you can use on bee stings. So, when the acid and alkaline react, you get a salt plus water. Now, the salt is harmless and the water is neutral, so it calms your stomach. Now, we can produce acids in other ways, as Femi is investigating.
Stella sent me here to investigate a very useful acid and alkaline reaction. Now, I know it involves an alkaline substance called soda lime, but as for the acid, well, she says a man called Martin Sampson's producing that. The only trouble is, there's no sign of him. Martin, now you're obviously a diver. I don't get what that's got to do with acid and alkali chemical reactions.
OK, I'll give you a clue. On my back, there's a device called a rebreather. It allows me to stay underwater for at least 3 times longer than an ordinary scuba unit. But in order to do that, I'm recirculating the gases that I'm breathing. It's a great piece of kit, produces very few bubbles, Wildlife photographers like it. NASA even train their astronauts on it. Well, Femi, here are all the bits and pieces of my rebreather.
Well, it looks very different from the sort of diver's tanks you usually see. What's so special about this one?
Well, that's right. When you normally go scuba diving, these fellas are used, huge cylinders, lots of air, but they're not efficient. Every time you exhale, they produce lots of bubbles, which scares fish, makes them difficult to photograph, and also means that the air doesn't last very long either. So instead, we've got a rebreather, and this allows me to breathe air through this tube, and I breathe it through the mouthpiece. When I exhale, the waste gas goes back down the tube and back into the set.
When we breathe in air, our bodies use some of the oxygen in it, and we then breathe out air containing the unused oxygen and the waste product, carbon dioxide. The rebreather allows the diver to rebreathe the unused oxygen, but not the carbon dioxide, which would be dangerous. It can do that because of this canister. Inside the canister are soda lime crystals, which turn universal indicator blue, showing that soda lime is a strong alkali.
We have the soda lime crystals, which are reacting with the carbon dioxide, neutralising it. The carbon dioxide does not come back out of this spout here.
Right, so if the soda lime, which is alkaline, reacts in some way with carbon dioxide, that means that the carbon dioxide that we breathe out must be acidic. Well, there's only one way to check if that's the case, universal indicator. And yes, my breath turns the indicator orange, meaning it has a pH of about 3. So the carbon dioxide we breathe out is an acid. And we already know that the soda lime in the rebreather is an alkali. So we have a reaction. The acidic carbon dioxide and the alkaline soda lime react to give us salt plus water. But how safe is the result of this reaction?
The salt is calcium carbonate, which is chalk and completely harmless, and the water actually comes back as water vapour in the rebreather and is rebreathed by the diver. That's useful because it helps to stop the diver from getting dehydrated.
So is this a new idea then?
No, this has been around for centuries, the reactions between acids and alkalis. It's just relatively recently that we've been able to incorporate it into diving equipment.
And that's a very useful acid and alkali reaction when you're 10 metres underwater.
There. That should hold that. Still plenty of work to do, but before I go, here's something for you to think about. A nettle and a dock leaf. Now, the nettle will sting, but the dock leaf will soothe the sting. So what's happening?
Well, there must be some sort of chemical reaction going on. One must be acid and one alkali.
I'm confused. If one neutralises the other, but the nettle stings, then why doesn't the dock leaf sting too?
Maybe the nettle sting is a stronger acid and the dock leaf a weaker alkali. So, we need more of it to neutralise the sting.